All
right, y'all. So like I said, 9.1 deals with what we call the composition of functions. So this section is really for people that are probably getting ready to go into physics classes and maybe chemistry type classes where you're dealing with a lot of formulas. So let me give you our definition of this. So y'all, the composition of functions is when one function is used as the variable replacement for another function. So what I mean, instead of putting in just maybe an X or a number for that variable, we're putting in a whole function for that variable, okay? So they got two styles. We got F compose G of X. So that's not a O, that almost looks like a little degree symbol, you know, like you got on Celsius and stuff. So that's just a little degree symbol. But this is basically F of G of X. So when I got this notation, this means that we put the function G of X into the F. So the function G of X is put into each X of the F of X function. So y'all, let me show you what I'm talking about. So this will be just an example of this. So say I'm given F of X equals 3x plus 2, and I'm given G of X equals something like x squared plus 3x. Then F of G of X so remember, we said we put the G of X into each X of the F of X. Well, this is my G of X right here, x squared plus 3x. So what we're going to do is put it into each X of the F of X so that this becomes 3 times x squared plus 3x. And then I still got my plus 2. And y'all, to simplify that, we just want to get rid of parentheses. So we'll distribute our 3. So I get a 3x squared plus 3 times 3 gives me 9x. And then at the end is my plus 2. So this is the composition of F composed G of X. And y'all notice, you're not putting in a single variable or a single number now. You're putting in a whole function for that X, okay? And then you just try to simplify it down. So y'all, they go the other way. We got G compose F of X. So this would be like G of F of X. So it's basically, instead of function G of X being put in the X's for the F of X, we're now going to take the F of X and put it into the X's of the G of X. So the function F of X is put into each x of the g of x function. And it's almost sort of like doing order of operations. When you write it like this, g of f of x, remember you always start with the innermost parentheses. You can't do nothing there, so you put that into the g. Same thing here. If you can't do nothing here, you put that into the f, okay? So let me show you an example of this. So let's say I'm given my f of x is, oh, how about it? X plus 2 and g of x. Oh, y'all, what I want here. How about 7x plus 3? So our g of f of x. So now remember, we said we're going to take the f of x, which is the x plus 2, and put it into the x's of the g. So that'll give me 7 times x. Well, x is now x plus 2. And then I still got my plus 3. So y'all simplifying this one, I'm just going to distribute my 7. So 7 times x is 7x. Plus 7 times 2 is 14. Plus my 3. And y'all look, this one actually got one more step, right? Because we got some like terms sitting right there. So this gives me a 7x plus 17. So this is going to be what they're going to have us doing. Now, I will say this. If numbers are given, so say they're wanting me to find, say, F composed G of 5 or something like that. So if numbers are given, we'll look at the two cases. So for F composed G of some number, so we don't know the number, we're just going to call it A. So if they give you a number, the first thing you're going to do, you're going to find G of A. And I'm going to put my number into the G function, see what that equals. Then I'll plug that value into my f of x. So I'm going to figure out g of a. Once I get that number, I'm going to plug it into the f of x equation. And y'all, it's the opposite if it's g of f. If it's g of f of a, well, the first thing we're going to do is find f of a. And y'all, so this sort of looks like they're going backwards to me. So you put the A in the F, you're going to get that answer, and then put that into the G. So y'all, that's what we'll do. Plug that value into our G of X. So we're about to hit some of their examples. So the first three, they're just going to give you numbers and have you sort of evaluate that. After those three, I'll show you about interval notation, and then we'll go through the last three problems they give us. I also, for this example, they want us to let f of x equal negative 3x minus 1. G of x equals x squared minus 2. They want me to find f composed G of 7. So they're giving me a 7 for my replacement. Now, y'all remember, if you wanted to write this as function notation, we're going to be finding f of g of 7. So writing it like this, we're going to innermost parentheses, which is our g of 7. So y'all, the first thing we're going to find is this g of 7. So g of 7 means I'm going to take this g equation and put a 7 in for that x. So that's going to give me a 7 squared minus 2. And also, let's see, that's what 7 squared to give us 49 minus 2. And then 49 minus 2 gives me a 47. So that's the first step. I now know that g of 7 equals 47. So my second step now is to find f of that 47. So y'all with me, y'all? The 7 went into the g, but now that 47 answer is going to go into the f. So f of 47 will be a negative 3 times that 47 minus 1. Okay? So we're basically putting this function's answer into my f. Well, let's see, what is that? Negative 3 times 47. I'm getting what? A negative 141 minus 1. So our final answer would be what? A negative 142. And y'all, that's the answer MathLab wants, is that final answer, okay? So basically, it's not bad, but it's doing what we did yesterday, but we're doing it twice. We're throwing it into one function, getting an answer, and then throwing it into the other, okay? All right, also this one, f of x is going to equal 2x plus 4. G of x is going to equal x squared minus 3x minus 5. All right, also on this one, they want us to find G compose f of 7. So it looks like 7 is my popular number for today. All right, so remember, this one's opposite, so this is like finding G of f of 7. So our first thing is to find that f of 7. So we're going to find f of 7. Once we get that answer, we'll throw that into the g. All right, y'all, so our f of 7, we're going to take the f equation, put a 7 in for the x. So I'm going to get 2 times 7 plus 4. All right, y'all, so let's see. 2 times 7, that'll give me what, a 14 plus 4, which gives me 18. So since f of 7 is 18, that means I now got to find g of the 18. Well, gee, oh, that's going to be a big number, y'all, because look at 18 squared. So I got 18 squared minus 3 times 18 minus 5. So you got two x's in G, so we have to put the 18 in for both of those x's, okay? Ooh, that's going to be a hard one for us. We have to break out the calculator, y'all, because we're from Arkansas. We quit at 12 times 12 here. So let's see. I think 18 times 18 on my calculator was like 324. minus 3 times 18, which is 54, and then minus my 5. Hey, also adding all these like terms together, I came up with, looks like 265. So y'all, that's the trick on them. Just look at the order they're giving you. Is it F of G or G of F, okay? So there's one more dealing with numbers. So F of X equals 3x plus 4. G of X is just going to be X cubed. They want us to find F compose G of a negative 4. All right, so got my two functions, looking for a negative 4. So this one would be like F of G of that negative 4. So we got to start with the G of negative 4 first. We know G is just X third. So that's going to be a negative 4 to the third. So that'd be like negative 4 times a negative 4 times a negative 4. You got 3 negatives, so it will stay negative. And then what's that? 4 times 4 is 16. 16 times 4, so that's going to make that a negative 64. So guess what? Since G of negative 4 is negative 64, we now need to put that answer into the F. So that means we're finding F of a negative 64. Now you also put that negative 64 into the X so that you'll have 3 times negative 64 plus 4. And you see what they're doing with these, right? This function notation we've been doing, they're just wanting y'all to realize that you're putting everything into these X's when you're doing this kind of stuff, right? All right, y'all, so let's see. 3 times negative 64 is a negative 192 plus my positive 4. So let's see, unlike signs, so the large one is negative. So 192 minus 4 gives me what, a negative 188? And y'all, that is our final answer. So y'all, that's the first three. They're going to give you numbers. You're going to plug them into one function and then put that answer into the other function. Now, we'll say the last three that we do, they're not going to have numbers for us, so all we can do is simplify those. But y'all, before we do those three last problems, we got to learn about interval notation. So interval notation is basically a shorthand way to write domains without me having to put X, such that X is a real number and X cannot equal whatever numbers. So the first thing about interval notation, in interval notation, all real numbers is represented by so we use parentheses. So y'all, if I'm going out the negative side of life and I keep getting more negative and I keep getting more negative, What do we say I'm headed off towards if I keep getting more negative and more negative? Oh, I think I heard it. Well, you're on mute. I see your lips moving, but it sounds like you're saying negative,
Infinity.
negative infinity. There you go. So negative infinity covers all the numbers toward the negative side. And then if I'm going out the positive direction, I'm headed towards positive infinity. So this is how we now write all real numbers in interval notation. It goes from negative infinity to infinity. That covers every real number there possibly could be. But now, what about kicking out numbers? So to exclude numbers, from the domain, we use the union. And y'all, in math, the union means and. And we use parentheses. So in math, if I use curved parentheses, that means it's not including the number the parentheses are around. If I want to include those numbers in a domain, I would use brackets. Okay. So, and we'll use brackets later on in life, but for right now, everything is in parentheses because we're excluding numbers. Okay. So let me show you an example. So for example, to exclude any number A from the domain, we would have, so they're always going to start at negative infinity. Now, and the reason infinity has parentheses instead of brackets is because infinity has no stopping point. So you can't contain it in brackets. It's got to always be parentheses, okay? But y'all watch how I kick out this A. So my domain goes from negative infinity up to the A, and then I'm going to use curvy parentheses and my union. So what this is saying, since I got curvy parentheses around this number, that it goes from negative infinity up to A, but it don't include the A. Then on the right side, it starts on the other side of the A, but it's still in curves, so it don't include that A. But from that A, I can head off towards
Positive infinity.
positive infinity. So anytime we're going to kick out a number, we do a union around that number, okay? And we're going to go left to right on these. So this is, so say we had a fraction and 5 made it undefined. We'd go from negative infinity up to 5, but not including it. And then from the other side of the 5 towards positive infinity, okay? Now, if you have to kick out two numbers, guess what? You'll have two unions. But you got to go in order from left to right. I think there might be one where we got two today. I'm not sure, but we'll find out. Oh, you also check out these last three examples. They want us to find f of g of x and g of f of x and the domain of each. All right, y'all, f of x is going to be x plus 17. G of x is going to equal x minus 17. So y'all, what I'll do, I'll find my f of g first, and then my g of f, and then we'll play with these domains, okay? So let's start with our f composed g of x. So remember, when it's f composed g, we're going to take the g function and put it into the f, okay? So we're putting g into f. All righty, so here's f, it is x plus 17. But we're not putting x plus 17 because we're replacing this x with x minus 17. So you're going to have x minus 17. That's putting g of x in for the x. But y'all, we still got a plus 17. So y'all, here's what I did. I took this right here and put it in for that x. Okay?
So would it just be X then?
It's just going to be x on that one. Good job. All right, so that's the simplified version of that. So let's do g of f of x. Well, that's the other way. This time, we're putting the f into the g. So you're going to take this x plus 17 here, and you're going to put it into the x on the g. So you're going to get x plus 17 minus 17.
Still just going to be X.
So that's just going to be an x also. This is the only one that works out like that. That's just because one's adding 17 and one's subtracting it. So here's my question is, here's my f of g. We had x minus 17 plus 17. That simplified down to an x. What is the domain of this f composed g of x?
All real numbers.
All real numbers. So now that'll be what? Negative infinity to a positive infinity. Because y'all, guess what? I don't see no fractions here. And fractions was the only thing we were worried about. All right, what about the domain of g composed f of x?
Same.
Same thing, y'all. So negative infinity to r positive infinity. So like I said, if you don't have any fractions on these functions, you don't have any restrictions. Okay. So y'all see that's what they're going to do. You have to find the f of g, the g of f, and then just sort of look at your domains real quick, okay? Now this one ain't going to be quite as easy just getting the x's on it, okay? So we're doing the same thing, but look here, f of x equals x plus 3. G of x equals 2x squared minus 5x minus 3. Now we'll say one of these will be a little bit trickier than the other, but let me start with f composed g. So this time we're putting g into f. So I'm putting all three of these parts from the g into that one x. So instead of x plus 3, you're going to have 2x squared minus 5x minus 3. That's putting my g of x in for the x, but y'all still got a plus 3. Well, that looks like it's simplified down a little bit.
So it would just be 2x squared minus 5x.
2x squared minus 5x. Yep. because them threes sort of canceled out there, right? All right, so that was done. So let's play with, I'll tell you, this one will be a little trickier. G compose f of x. You know what that means? We're putting the f into the x's for the g. So y'all, you're putting this x plus 3 in for both of these x's. So you're going to have 2 times x plus 3 squared minus 5 times x plus 3 minus 3. Now, y'all ain't gonna lie, the biggest mistake I get on this is people want to distribute that 2. No. Second mistake is people want to distribute the exponent and make that an x squared plus 9. No. So let me go to the side here, because what you got to do is actually FOIL this out, the x plus 3 squared, okay? So what I would do, bring down my 2, and then I'm going to FOIL this out. So I'll FOIL that out over here on the side. Because when you got stuff being added or subtracted and an exponent following, you got to write that twice and FOIL it, okay? So y'all, that'd be x times x is x squared. X times 3 is 3x. Then I'm going to distribute to 3 times x is 3x. And then the 3 times 3 gave me 9. So adding like terms, this will turn into an x squared. 3 and 3 give me 6x plus 9. Y'all, this is what we got to put in place of that x plus 3 squared. X squared plus 6x plus 9. And then I got my minus 5 times x plus 3, and then minus 3. Okay, so we just sort of work this part first. So now I'll get rid of both these parentheses by distributing the numbers in front of them. So you should get a 2x squared. What's that, a 12x plus an 18. And then I'll distribute negative 5 times x is negative 5x. Negative 5 times 3 is negative 15. And then at the end is a minus 3. All right, y'all, so time to add like terms. So I know I got a 2x squared. Let's see, on our x's, I got what, 12 minus 5. That's going to be what, a positive 7x. Oh, y'all look at that. I think the numbers are going to 18 minus 15 is 3 minus 3. So the numbers are canceled. Good job. So the first one equal 2x squared minus 5x. Second one, 2x squared plus 7x. So how about my domain for f composed G?
All real numbers.
All real numbers, because y'all, there's no fractions in this. So that's going to be negative infinity to infinity. So how about the domain of the other one? Yeah, we got a lot of foiling and stuff, but we don't have any fractions again. So once again, that will be negative infinity to infinity. But y'all do realize they're not going to give me everything like that, right? So y'all watch this last problem they're hitting us with. And ooh, this last one's sort of tricky, simplifying everything. It's going to bring back all your knowledge from fractions, I think. So y'all look at this. F of x is 2 over 1 minus 9x. G of x is going to equal 1 over x. So y'all, they threw two fractions at us. So let's play with f of g first. F compose g of x. So remember, I'm going to put this g function 1 over x. I'm putting it in place of that x on the f function. So that's going to give me 2 over 1 minus 9 times that 1 over x. Okay, so you just put the g into the f there. So y'all, to simplifying is the tricky part on this. First thing you want to do is multiply that 9 times that 1 over x. So that's going to give me my 2 on top over my 1 minus. Well, y'all remember, if you multiply a number times a fraction, you can put a 1 under the number, and you're just multiplying straight across. So top times top, bottom times bottom. So that's just going to give me a 9 on top, and then my x on the bottom. So let me explain what we're about to do. This here is called a complex fraction because you got a fraction inside of a fraction, okay? So we're not allowed to leave the answers as complex fractions. So we got to try to get rid of this fraction. So let me ask y'all this. There's an x in the bottom of that fraction. If I want to get rid of this fraction, I'm going to multiply everything by x. So y'all, I'm going to multiply everybody by x. To eliminate that fraction. Or how about the bottom fraction? So y'all watch this. Now remember, when you multiply, everybody gets multiplied in a expression, okay? So we're going to multiply the 2 by x. We're going to multiply this 1 times x. And then we're going to multiply this 9 over x times x. Now, the only thing I'm worried about, y'all, what happens to these x's right here?
Cancel.
They're going to cancel. Now, on top, 2 times x is 2x. On bottom, you got a 1 times x, which is x. So y'all, since y'all canceled those x's out, all that's left is a 9. So it now looks like a normal fraction. You got a numerator and a denominator. Nothing else we can do to that. So that would be our final answer for that one, okay? So y'all want to do g of f of x next. Then we'll play with our domains. So g of f of x, we're going to put 2 over 1 minus 9x in for that x on that g. So the top will be 1 divided by, well, instead of x, we now have a 2 over 1 minus 9x. So y'all with me, y'all? The first one I put g into f, the 1 over x in for that x. The second one I put the f into the g. Now this one's not as bad to simplify. Since this is basically a 1 divided by a fraction, y'all remember the little rule? I can change this division into multiplication and flip the bottom fraction, right? So 1 divided by 2 over that equals 1 times, and then you flip the fraction so that you get 1 minus 9x over 2. And y'all, the reason I'm doing these differently is because this one had a small fraction inside of it, to where this one's just a top being divided by that bottom. Now, 1 times anything is the anything. Well, we can't do nothing else with that, so we're going to have our final answer. But notice, it's no longer a complex fraction. You don't have fractions inside of a fraction. You just got a regular fraction with a numerator and a denominator. Well, let me ask y'all this. Is this domain going to be all real numbers?
No.
No. So we have to find spots where we have to look at. Y'all see right here, you got an x in the denominator. What can that x not equal?
9.
Well, 9 divided by 9 is 1.
But you would do it from the 2x
Exactly.
at the bottom, not that one.
Uh-huh. Now, yeah, you're looking at this one. So x cannot equal 9 because of that. What can this x not equal?
0.
Oh, what did y'all just say?
0.
0. Right, at this point, if you put a 0 in, 9 over 0 made that undefined.
Mhm.
Now, once you went through and simplified it, you couldn't have a 9 here because 9 minus 9 made that one 0. So you got to look at all places where you got a fraction and kick out any of them numbers that are going to make it undefined.
Oh, so it won't just be your final answer.
It won't just, no, because right here, when you plug in that 1 over x, so you got to look at that one also, okay? So you just sort of got to look through here. And so the 1 over x, basically the 9 over x was the same thing. We just multiplied it out. But that still can't be a 0 here, okay? And if I put a 0 into this formula, I'm going to get a error message. Now, the final answer couldn't be a 9 because 9 minus 9 made that part 0. So we're kicking out 2 numbers. So we're going to start at negative infinity. Now you got to go left to right on the number line. So the first number we're going to kick out would be the 0. So we're going to union around 0. So y'all, from 0, we're cruising until we hit 9. We got to kick the 9 out. So we're going to union around that 9. So the union kicks out to 0. The union kicks out to 9. From there, I'm headed towards
Infinity.
infinity. There you go. All right, how about this one?
I'm lost on this one.
And y'all, I'll tell you the only part, I'm not worried about the final answer. All that's on the bottom of that is a 2, right?
Mhm.
All I'm worried about on this one is what's happening right here. This 1 minus 9x cannot equal 0, remember? So for this one, I might just set that 1 minus 9x equal to 0 and actually solve it. By solving it, I know what that x cannot equal, okay? So what would we do? Subtract 1. I get negative 9x equals negative 1. And then divide by your negative 9. So that gives me a positive 1x. That's going to give me a positive 1/9. So if you put a 1/9 here, the 9's cancel. 1 minus 1 would make that 0. So we got to kick out the 1/9. And y'all, that looks like the only thing here, right? That's the only place I even got a variable in the denominator is on that one section. Like I said, the final answer only has a 200. So this domain going to start at negative infinity. You're cruising until you hit 1/9. You're going to union around that 1/9 to kick it out. And then y'all were headed off towards positive infinity. Now I want y'all to notice at this point, every domain we've done is starting at negative infinity and going towards positive infinity. All we're doing is finding numbers that we're kicking out, okay? So this is interval notation. What we was doing yesterday with the domain, that is what we called set builder notation. All right, y'all, question on that? Well, do y'all like the algebra better or the graphing?
Graphing.
And I will say, y'all are in a summer math class, so you know you're just going through so much material quick here, right? Y'all, that was 9-1, so next is 9-2. And this deals with inverse functions. And y'all, to me, inverse functions are like their opposites, like multiplying and dividing, adding and subtracting. It's sort of the functions that undoes the original functions and stuff. Oh, y'all, it's almost break time though, so I'm going to pause this stuff. So let me share my screen here. All right, so before we get into actually finding inverse functions, we're going to look at how to find the inverse of a relationship. So y'all, to find the inverse of a relation, we switch the x and y values. So this is getting you used to the idea that on inverses, you basically switch x's and y's around, okay? So on this one, they want me to find the inverse of the relation. So the relationship they're giving me is negative 9-2, 6, negative 6, negative 5-9, and 5, negative 5. So our answer for this one. Now, MATLAB will give you the curvy parentheses, but y'all, you got to put all the other parentheses and all the commas in it. So all we got to do is switch the x and y values. Well, remember, this is x and y for each of these ordered pairs. So if this is x and y and I'm going to switch them, my first point will become 2, negative 9. My second point, switching those, will give me negative 6, 6. My third point would be what? 9, negative 5. And then finally, switching that, I get a negative 5, positive 5. And y'all, that's all you do to find the inverse for a relation. If you given a set of ordered pairs, you're just switching them around. So watch this. On this one, a little trickier, but they want me to find an equation of the inverse relation. All right, y'all, so the problem they're giving me is x to the third times y equals -3. You know what they say up here? We just switch to X and Y. So if we switch to X into Y here, this now becomes a Y to the third times X equals -3. So y'all are getting an idea on these inverses? All I'm doing really is switching those X and Y's around. Now, so we're going to start writing a little bit of definition here. So we're going to start looking at functions. So for a function to have an inverse, the function must be 1-to-1. Now, what 1-to-1 means is now, do you remember on the functions, we said in order to be a function, all the x values could only have one y value? Well, for it to have an inverse function, that means that each y value can have one and only one x value. Okay? So that means the y's can only have one x value. So to check that, so to check for 1-to-1, we use the horizontal line test. And y'all remember, horizontal lines are the ones that go straight across left to right, okay? Whoops, mine's not too straight, but y'all get the idea. There. So horizontal line straight across. So what that means is a function is 1-to-1 if a horizontal line can intersect the graph just once. Okay. If my horizontal line intersects that graph more than once, it's not 1-to-1. Same thing with the functions. The vertical line couldn't intersect the graph more than once for it to be a function. Same thing with the horizontal line, okay? So we're just going to play with this 1-to-1 stuff real quick. So y'all, these examples will say using the horizontal line test, determine whether the function is 1-to-1. All right, y'all, so let me draw this first one here. See all this graph? just sort of slowly goes uphill to the right. But notice, if I do a horizontal line, it intersects it once. Horizontal line intersects it once. Horizontal line intersects it once. So since this horizontal line only intersects that graph once everywhere, this would be yes. 1 to 1, because all these y values here only have one x value, okay? What about a upside down parabola? Is that 1 to 1? Well, y'all, here's my horizontal line going across it, and look, it intersects it on this side, it's intersected it on that side. Anywhere I go, it's intersected it on 2 points on that line. So since these y values here are getting 2 different x values, this one would be a no on that, okay?
But it would be a function.
But it is a function. All right, so this one's sort of funny looking. It has a part going upside down here. And this side is sort of going up, and this side is sort of going down. We'll look at these graphs later on in life. But is it 1 to 1?
Mm-mm.
No, because horizontal lines are intersecting it twice on top and bottom. So good job, that'd be a no. All right, also they had one more. What about this little squiggly lines that we were drawing?
Yes.
Yes, because if you draw these horizontal lines, it's only going to intersect it once everywhere. So that one would be a yes. All righty. So that was all setting us up so that we could actually find inverses of a function. So y'all, we're about to play with these functions here. So finding the inverse of a function. Now y'all remember, function notation is f of x, right? Inverse function notation is the f -1 of x. So if you see this notation where they got the -1, that means this is the inverse function. F of x is the actual function, okay? So y'all, this is going to be the steps to finding those inverses. So the first thing, we're going to replace f of x with y. Because remember, f and x and y are the same thing. But now we're going to take it out of function notation and use a y for it. And y'all, the whole reason I'm turning that f of x into a y is because now I'm going to switch that x and y. So switch the x and y variables. All right, y'all hang on. I gotta let these dogs out of here. Come on. Yep. All righty. All right, so we switched the x and y variables around. At that point, we're going to solve for the y variable. So y'all, at that point, I'll have it solved for the new y variable. Now I'm going to replace the y with my inverse notation, my f negative 1 of x. Now, here's the thing on this one. To have an inverse, a function must be 1-to-1. Now, I'm not going to lie. All the homework problems that start at number 7, they're all 1-to-1, okay? So don't put not 1-to-1. They are definitely all going to be 1-to-1. So these examples will say, for the following functions, A, you're going to determine if it is 1-to-1. And then B, if 1-to-1, find its inverse. So you can just graph them real quick on your calculator to check if you want to. But like I said, they're all 1-to-1, okay? So y'all, we're starting at number 7 here. They're giving us f of x equals x minus 6. If you was to graph this, you would see that it would be a straight line like all them straight lines we've been drawing with the x's, right? Well, this is just a straight line, so it's definitely 1-to-1. So what do we say was our first step? We're going to replace the f of x with a y. So y'all, I'm going to replace f of x with y. So that's going to give me y equals x minus 6. So then what do we say? Well, we said, hey, you're going to switch those variables now. So now we're going to switch the x and y. Well, that's going to give me x equals y minus 6. So y'all, you got one move to get that y by itself.
Hey,
Because we want to get this 6 moved over. So what y'all doing with that? Add 6 to both sides? So y'all look at that. I get my x plus 6 equals my y. So I'm now solved for the y. So now my final step, replace that y with the f inverse notation. So I get f negative 1 of x equals my x plus 6. Now y'all notice a few things about this inverse. The original function was subtracting the 6. Look at my inverse. It's adding the 6. You'll notice that the inverse functions have opposite operations than the original function. So y'all got a question on that one?
is that it? Like the final answer?
That's the final answer. So they're not too bad. I'm just trying to. All right, y'all. So let's go to number 8. All right, how about this one? F of x equals 7x minus 9. Well, if you graph that, that's another straight line. So it is definitely 1 to 1. So the first thing we're going to do, replace that f of x with a y. So I'm going to get y equals 7x minus 9. And what do we do next? We're going to switch the x and y. I'm just going to sort of write my instructions down on a few of these, and then once y'all get the hang of it, we'll just work them. So that's going to give you x equals 7y minus 9. Now notice, I'm not moving the number in front of the y. I'm just switching that x and y around. So now we want to solve for y. We ought to solve that. We need to move that negative 9 over. So we're going to add 9 on the first step. So you'll get your x plus 9 on the left side. That's going to equal to 7y. Now turn the 7y into 1y. So I'm going to have to divide this thing by 7. So that means we're dividing both sides by 7. So y'all, that 7s will cancel, making that a 1y. And y'all, we can't do nothing with that. So that's going to stay x plus 9 over 7. Last step, replace the y with your f inverse notation. Now, y'all, MathLab will give you the f negative 1 of x. All you got to do is put in the answer. And that'll be what? The x plus 9 over 7. But look at all the counter moves. They were subtracting 9, we added 9. They were multiplying by 7, we divided by 7. You're always going to see the counter moves there, okay?
Will it always be the opposites of what it is?
Basically, those operations will be. Now, they're going to look a little different, than the original, but it is those opposite operations on them, okay? All right, y'all, so watch here. Here's a sort of tricky one. F of x equals 8 over x plus 1. So if you graph that, you'd see it'd be sort of a curvy line, but it is 1 to 1, okay? So replace the f of x with a y. Once you turn that f of x into a y, you're going to switch that x and the y around. So y'all, this would give us x equals 8 divided by y plus 1. So here's my situation. I can't solve for the y while it's in the bottom of a fraction. So y'all, to move this y plus 1 from the bottom of this fraction, you're technically going to multiply both sides by that y plus 1, okay? So I'm going to multiply both sides times y plus 1. So y'all look here, what's happening on this right side? What are you going to do with these y plus 1s on the right side?
Cancel.
They're going to cancel. Now, I'm not going to distribute this x. I'm going to leave this a y plus 1 times that x is now equal to that 8. So y'all listen, we're solving for the y. So we're not going to distribute this x. Since this x is being multiplied, what you want to do is come in and divide both sides by that x. Because by dividing by the x, guess what? Those x's cancel. All that's left over here is a y plus 1. So do y'all need parentheses still? No, that's just going to be a y plus 1. And over here, all that's left is the 8 over x. So do y'all see what happened in the long run? You see what I got here? X equals 8 over y plus 1. Down here, I got y plus 1 equals 8 over x. Basically, all we did was flip-flop that whole thing. All right, y'all, how are you going to get this y by itself now? Well, they're adding 1, so there you go. Subtract 1 from both sides, that gives you y equals 8 divided by x minus 1. All right, y'all, last step. Change that y back into F inverse notation. And then your final answer is 8 divided by x minus 1. So a little bit wild on some of these, but they get there, okay? Probably on 10 now. All right, y'all. F of x equals x cubed minus 4. Well, if you used to graph that, it'd be one of them squiggly lines, but it would be 1 to 1. So you're going to replace the f of x with a y. All right, now that I made that f of x into a y, we're going to switch them around. So you're going to get x equals y to the third minus 4. Okay? So here I made f of x a y. Here I switched the f and x. I mean the x and y. Now I'm going to solve for the y. So you want to get this y to the third by itself. So first off, we're going to add 4 to both sides. So y'all look at that. That'll give us an x plus 4 over here equal to a y to the third. So y'all, I guess the question of the day is, how can you turn a y to the third into a y?
Divide.
Well, what would y'all divide by? So let me recall y'all on something over here. Say I got some variable a raised to the n power. So n would be like my 3 here. So this is like y to the third. If I want to turn this into just the a, I would take a square root, cube root, whatever root matches that exponent. Because what happens is, if the exponent matches the root you're taking, those cancel, and all that's left is your a. So the question is, if this is a y to the third, I'm going to take a cube root of both sides. So y'all watch this. A cube root of x plus 4 will equal a cube root of y to the third. Y'all, we got it right here. If that index matches that exponent, well, my index matches my exponent. So that right side is just going to equal to y. because this stuff sort of cancels out. Can't do nothing with this side, can we? So that's just going to say a cube root x plus 4. You know my final step? F negative 1 of x equals this cube root of x plus 4. So here's the thing, y'all. Exponents, their inverses is square roots, cube roots, fourth roots, whatever. But this index of this radical will match that exponent, okay? All right, so that'll be, and I'll do a little bit of this square root stuff in the support for this section. All right, y'all, watch this. F of x equals 2x squared plus 3. Now listen, this one says x has to be greater than or equal to 0. Now let me show you why they're saying that, okay? I'm just going to show you why they're restricting your domain when they do something like this. But y'all, let me show you why. So I'm just going to go to calculator. I'm just going to graph that function. 2x squared plus 3. So I'm just going to graph it without any restrictions so that y'all see what's happening. Is that 1-to-1?
Mhm.
But now, notice what they told me. I'm going to go to the window here. They told me that the smallest x could be 0. That's what they meant when they said x has to be greater than or equal to 0. Okay? So that means the smallest x value can be 0. But watch what happens when I graph that. Is that now 1-to-1?
Like just looking at that section?
Just looking at that section. You see how this is just a little curvy line going uphill now? So since they restricted my domain, I don't look at this left side. I only look at the part from greater than 0. So if they're restricting the domain, telling me it's got to be greater than 0, then it is definitely 1-to-1, okay? So that's what they mean when they're doing this stuff. Because they want it to be 1-to-1, right? So since we restricted it and we're only looking at that right side, it's 1-to-1. So we're going to replace the f of x with a y. We're going to switch the x and y now so that we get x equals 2y squared plus 3. And y'all, I'll tell you what, on this one, they actually gave you most of the answer. We just had to find the top part of it. All right, y'all saw that for the y. So first we need to move the 3 over. So we're going to subtract 3 from both sides. So I get x minus 3 equals 2y squared. Now, I want this y squared to be a 1y squared on this side. So I'm going to divide both sides by 2. So the left side is just an x minus 3 over 2. That's now equal to my y squared. So how can I turn a y squared into a y?
Wait.
And since that's a 2 there, we're just going to take square roots of both sides. So y'all, this left side, we can't do nothing with that. So that's going to stay a square root of x minus 3 over 2 equal to my y. So if you ever see a square root like this and it's not having a number up there, it's understood that this number is a 2, okay? So if there's no number there, it is a square root. So notice this. When I had exponents of 3, we ended up with cube roots. exponents of 2, we ended up with square roots, okay? Oh, and I guess my last step would be to do the inverse notation. But y'all check it out on this problem. MATLAB gives you this. MATLAB will give you this much of the answer. All you had to do was come in and put the x minus 3 there, okay? So they're not real bad. You just got to sort of keep up with the what they're doing to them.
What they're asking for them.
Mm-hmm. So what about this next one? I'm going to do one with a radical instead of an exponent. I'm just letting people catch up. I see some people still writing, so I'm going to let them catch up. So there's one more in this section, number 12. And then I'm going to show y'all the support because the support goes over stuff that's helpful in this section. All right, y'all. So number 12. F of x equals a square root x plus 4. So this would be like a slowly uphill going line to the right, but it is 1-to-1 on this one for sure. So let's make the f of x a y. So what am I doing next?
X equals square root of
Okay.
y plus 4.
So you're switching them around. Good job. Now let me tell you all a little trick about this. Since this y plus 4 is all up under this radical, you can't move that 4 by subtracting 4. Because numbers outside radicals can't add to numbers inside of radicals. So this y plus 4 is stuck until y'all can get rid of that radical. Well, let's recall something about this stuff. If radicals undo exponents, guess
Exponents.
what undoes exponents? I mean, what undoes radicals?
Exponents.
Yeah, if you had a square root of a, I could raise them both to the n, right? So that the exponent cancels the radical, and this will just equal my a. So if I want to get rid of this, we're going to square both sides, because remember, that's a square root. So we're going to square both sides. Well, y'all, this is just going to stay at x squared. But the right side, the exponent cancels out the radical. So all that's left is a y plus 4. Which means my last step now to get to y by itself is to move that positive 4 by subtracting 4. So y'all, when I get a x squared minus 4 is now equal to my y. And then I'll just put it into f inverse notation. And f inverse of x will equal x squared minus 4. So you'll notice radicals end up with exponents. Exponents end up with radicals. You'll notice a lot of times the opposite signs on the adding and subtracting and all that fun stuff, okay? But yeah, that's what we're doing to you in that section, okay? All right, y'all, so I'm just going to look at the support for that section just to show you what that's about. I think this is just what our second support, I think, of the year. So the first thing we have to solve where you got a fraction equal to a fraction. So solving equations of the form A over B equals C over D. So I got fractional equations. So y'all, to solve these, the easiest way to get rid of these fractions is what we call cross multiplying. The top of the one fraction multiplies by the bottom of the second fraction, and the bottom of the first fraction multiplies by the top of the second one. This is called cross multiplying. Doing that, you get AD equals B times C, okay? But guess what? The fraction's gone at this point. So on these ones, we're just going to solve. I'll do a couple off the beginning. So y'all, this one has 6 over x plus 1 equals 5 times x minus 3. Now, this only works when you got one fraction equal to a fraction or one fraction equal to just a number. Because remember, a number I can make look like a fraction by putting a 1 under it, okay? Now, we're going to cross multiply. The 6 on top has to multiply by both of those on the bottom. So that's going to be 6 times x, which is 6x. 6 times -3, which is a -18. That's going to go on the left side. On the right side, this 5 is going to multiply by both of those on the left side. So that 5 times x gives me a 5x. And then the 5 times 1 gives me a 5. Now look at that, fractions are gone. So I'm probably going to slide my x's over here and my numbers over there. Okay, so let me move the x's first by subtracting 5x. So y'all notice if I do that, 6 minus 5 leaves me 1x minus my 18. On the right side, all that's left is that 5. And y'all look at that, my final move.
Add 18.
Add the 18, there you go. So I get an x is
23.
23. So if you put a 23 in for those x's, both sides would be equal, okay? All right, what about this one? X plus 5 over x equals 4 over 3. But y'all, same thing, right? This x plus 5 up here, both of those are going to multiply by that 3. So that'll give me what, a 3x plus 3 times 5 is 15. Now, the right side is not that bad. That's just what?
4x.
4x. There you go. Now, I'm not going to lie. This one is, the way it looks is a little tricky, but there's one move. If you do one move to this, you'll be done.
You just subtract 3x.
There you go. Subtract 3x. So that cancels, leaving me a 15 on the left side. But look at that right side. 4 minus 3 is 1x. So if you put a 15 in here, 15 plus 5 is 20 over 15. And 20 over 15 reduces to that 4/3. So those would be equal and we're done, okay? So y'all with me on the fraction equal to fraction, cross multiply, solve it, and be done. What about solving equations with radicals. So I'm talking about stuff like this, square root of n stuff, okay? So there's a little property that tells us if A equals B, then A to the n equals B to the n. So this goes back in it. What it means is if I raise one side of an equation to an exponent, I got to do that to the other side. Okay? And it's going to be the law anytime you got equations. What you do to one side of those equals, y'all, you got to do to the other side, okay? So here's my few steps I use when I'm solving these equations. First thing, you want to get that radical on one side by itself. So get the radical by itself on one side or the other. But y'all, if you remember when we were solving that while ago, that's why first thing I tried to do was get that radical all by itself. Remember, we added and subtracted to get numbers moved over. So I'm going to get this radical on one side by itself, okay? Then I'm going to raise both sides to the exponent that matches the radical. So if it's a square root, I'm going to square both sides. A cube root, I'll cube both sides, and so on. And at that point, you're going to solve for the variable. Because once you now really at that point, that could be the last step. Now, if you had something under the radical, like an x plus 5 or something, then you would actually ask to solve it, okay? So solve for the variable if needed at that point. Sometimes it'll be done at that point, okay? And then always check if needed. All right, so they got a few doing that, and I just wanted y'all to see some of these examples, okay? And y'all, these will say solve. I got a square root, 8x minus 9 equals 1. Now notice, this radical is by itself because that 8x minus 9 is under that radical, okay? So if I want to get rid of this radical, my first step is to raise both sides to the second power. So I would come in and square my 8x minus 9, which means I'm going to square that 1. Well, this left side, that radical cancels that exponent now. All that's left on the left side is our 8x minus 9. Oh, look at that. 1 squared, 1 times 1 is 1. So see how since this one had stuff being multiplied and subtracted under the radical, you actually got a couple steps here to go. So first of all, I would move that negative 9 by adding. So that's going to give me 8x equals a positive 10. And then y'all, the final step.
Divide.
So that cancels and x equals 10 over 8. But that will reduce
5/4.
5/4. There you go. Okay. So y'all, that's all they're doing, just getting you used to solving these little questions in support so that when y'all hit these radicals on the actual college algebra part, you'll be good to go. So now look at the difference. Over here, everything was under the radical. Well, over here, everything ain't under the radical. That 2 is not under that radical. So remember the first step I said? Y'all need to get that square root of 5x by itself.
So add 2.
Oh, you're so close. You said add 2, but we
Subtract 2.
Right.
there you go. There you go. So look what's happening. That brings down that square root of 5x. And let's see, 15 minus 2 is 13. So the radical's by itself. So what you think I'm going to do next?
Exponent 2.
So since that's the square root, we're going to square both sides. Oh, so let's see, that canceled. I got my 5x. Oh, y'all, that might be tough. Once again, I said we quit at 12 times 12 in Arkansas. So what's 13 times 13? See, I told y'all. Y'all quit 12s in France too?
169. 169.
Uh-huh. Hildegard, did y'all quit at the 12s in France?
Yes.
That's worldwide, I guess.
Oh.
All right, y'all, I got one more step. And we'll divide both sides by that 5. So that cancels. X equals a 169 over 5. So these were square roots. Let's throw a cube root at you. Cube root of x equals -3. Well, y'all notice this cube root is by itself. So we're going to raise both sides to the 3rd power. So we call that cubing. We're going to cube both sides. So y'all look at that. That cube root cancels with that exponent, leaving my x.
Negative 27.
3 to the 3rd power.
Negative 27.
So negative 27, okay? I tell you the truth, I don't mind these radical equations because once you get to squaring them and cubing them, they're gone. Oh, y'all, so another cube root, a cube root of x plus 5 equals 6. Now remember, you got to keep them squared away here like this one. Everything's under the radical. So we can't subtract 5 right off the bat. Y'all got to get rid of that radical first. And to do that, we're going to cube both sides. So the cube root of x plus 5 cubed equals 6 cubed. So y'all look here, the left side that cancels with the exponent. I got an x plus 5. So y'all 6 to the 3rd power.
216.
So 216. So when you got stuff added under the radicals, you usually got that last step to get that x by itself. So what y'all doing for your last step?
Subtracting 5.
So subtracting 5. So that cancels, so I'm going to get my x. And then let's see, 216 minus 5?
211.
211. And y'all, so just remember, they're just giving us this little support stuff to sort of help us when y'all are doing them inverses and having to solve the exponents or solve the radical stuff, okay? And then the one with the cross multiplying would have technically would have applied to the one where I had the square root and x plus 5 over 2 or whatever. So y'all questions on these? So y'all play with this 9-1 and 9-2. Anyone, if anyone started late, we're off tomorrow, remember? So that gives y'all a chance to catch up during the day before y'all do your fireworks and all that fun stuff tomorrow night. So just try to catch up. I will say Friday, we're going to be solving systems of equations. So those are going to be our longest problems of the year. Okay? Because we'll be solving equations with x's, y's, and z's in them. So 3 variables we're going to be solving for. So, y'all, let me stop this share on this. Everybody got this? All right, let me make sure I got everybody here real quick. Patricia left. I got Hildegard, Darren, John, Aaron. All right, I got all of y'all. So I'll probably start adding those participation points over the weekend, you know, so for y'all being here on these Zooms with me and stuff. All right, y'all. So I'm not seeing any questions. So y'all good?
I think so.
All right, y'all. So
Yes,
let me quit
sir.
this recording.